It is a great pleasure for me to present my work in this event. I know like this virtual meeting is not the best interacting form, but we can still like discuss science as we want. So the topic of my talk is topological phonons in oxide perovskites controlled by light. And the key information in this work is first, topological phonons are everywhere in oxide perovskites. And second, we can use photoexcitation to control these topological quantum states. We probably already know that the topological states in the electronic system have been well studied in different like Dirac semi-metal or topological insulator. And recently, people just realized that in phonon systems, we can also observe this kind of topological features. So I'll give a brief introduction first on the topology in electronic system, and then how we extend this idea into the phonon system. And then the key information is we find that these topological phonons are everywhere in oxide perovskites, and then we can use photoexcitation to control these topological quantum states. Our story starts from the Dirac equation. We know that Paul Dirac proposed an equation and to combine the quantum mechanics to special relativity. And in Dirac equation, if we see like the mass term equal to 0, we can get the linear dispersion for the energy of the band. That is how they get like special relativity combined with this quantum mechanics. And 90 years, nearly 80 years after the discovery of this Dirac equation, people find in graphene, in like a 2D carbon graphene, the low energy excitation near the Fermi level will just behave like the Dirac cone. So we can see like the linear dispersion in graphene. And 10 years after the discovery of graphene, people find that there's a three-dimensional counterpart of this two-dimensional Dirac cone, which is called Dirac semi-metal. That means if you go to like from X, Y, and Z direction, you can always observe such a Dirac cone in different directions. And this is the topological feature of this Dirac equation and Dirac cone. And such Dirac cone is actually related to the band crossing rule, which has been proposed first by Phonons and Wigner 90 years ago in diatomic molecules. And this band crossing rule was later extended into the energy band of solids, of solid crystals by Hering in 1937. And then recently, people realized that we can associate a topological invariant with this band crossing point. And sooner after the discovery of graphene, people always predict first like Dirac semi-metal and Weyl semi-metal, and then using experimental techniques to verify all this low energy excitation can hold certain topology. And the band crossing rule in that system was firstly, as we mentioned before, proposed by Phonons and Wigner. So if we consider by atomic molecule system, in a separate way, if we only consider two isolated atoms, there will only be energy levels of the system. And when the two atoms become closer to each other, the different energy levels will hybridize with each other, and sometimes be like band crossing happen, and sometimes they form more or less like an energy band to the system. This is all controlled by the distance between these atoms. And if we want to study a band crossing rule, we can only focus on like two bands, because in a band crossing, there's only two bands that are relevant to this physical phenomenon. So if we consider two bands that are equal to each other, we can just write the 2x2 Hamiltonian and let them eigen energy equal to each other. That means we get the diagonal term of the Hamiltonian equal to 0, and also the off-diagonal term the diagonal term equal to each other, and the off-diagonal term equal to 0. Unless this formula is satisfied, we can get the band crossing rule. The thing is, we have two equations, which is first the diagonal term equal to each other, and second the off-diagonal term equal to 0. However, the thing is we have only one tuning parameter, that is the distance between these two separate atoms. So we have one parameter for two equations that must be unsolvable, unless one of these conditions are automatically satisfied. For example, the off-diagonal term can be equal to each other that the off-diagonal term can be equal to 0 if the two-wave function of these two states belong to different irreducible representations. Therefore, as long as we have two irreducible representation of the bands, we can form a band crossing without them being gapped. So when they gap, they hybridize with each other, and this eigenenergy will not be equal to each other, which is well established. And such kind of band crossing was actually proposed like nearly 200 years ago by Hamilton in this like biaxial crystals. He finds that the wave surface of these states forms something like a Hamilton core. And this was recently being rediscovered by Michael Berry in this kind of systems. And what he finds is that this band crossing actually forms some fermionic properties, and this two direction of the wave vector can be seen as the irreducible representation of two wave functions. Therefore, we have a band inversion rule, band crossing rule that can be related. The key information is if the two-wave function belong to two different irreducible representatives, we can automatically get the band crossing rule. And I'll just show one example of this band crossing rule. For example, consider a mirror symmetry in the crystal. And the mirror symmetry gives us the eigenvalue of -1 and +1, for example, here. And that means we can label one band and the other band. We can label bands on their mirror plane with -1 and +1. And if we have a band crossing, that means the two eigenenergy are equal to each other. And when the two bands belong to the same irreducible representative, for example, if they all belong to -1, these two gaps will be hybridized. These two crossing will be hybridized, and there will be no band crossing formed in the system. However, if the two crossing bands belong to two different irreducible representations, the band crossing will be protected by the symmetry of the system. Therefore, we have the band crossing, we have the topologically protected band crossing in that system. And if we consider one example here is our lead oxide paper, what we find is that the system have two mirror symmetry in the mirror plane of Kx equal to Ky. And when we have a crossing band here along the gamma z and gamma m direction, this gamma z and gamma m belong to the mirror plane of the system. That means as long as we have the band crossing in that mirror plane, there will be automatically form a null line in that system. And that null line, and we call this a null line semi-metal. To understand why this band crossing can form a line, we can simply consider there's one mirror plane. So we have one equation Kx equal to Ky, and also a crossing band. That means we have another equation that makes this eigenvector and eigenenergy equal to each other, and we have three variables Kx, Ky, and Kz. So we have two equations but three variables. The solution space must be the one-dimensional line. That means we'll always have like no line and no ring in that mirror plane. And the no line and no ring is always pinned on that mirror plane. So in our lead oxide paper, there are two disadvantages of this paper. The first is because these topological states belong to the electronic system. And we all know electrons are fermions, so they obey Fermi-Dirac distribution. That means for experimental verification, we would require that this topological quantum stays near the Fermi level of the system. So that means if we have some defects or some Fermi level shift, it will be hard for experimentalists to observe these topological features. The other thing is that electrons can be like there's spin-optic coupling because electron carries certain spins in that system. And the thing is, whenever we consider spin-optic coupling, we can't consider the original two-band model. For a two-band model, when there's a no ring form, we only need a 3-Pauli matrix to vanish at the same time. But that's just for a spinless system. When there's a spin-optic coupling effect, we need to consider a 4-band model into the system. That means we need 15 Dirac equations to vanish at the same time to have a no line. So here in our lead oxide paper, we find that the system is gapped because of spin-optic coupling. And on the other high symmetry line, there's certain screw symmetry that protect this band crossing, but that's another story. So in electronic system, we have two disadvantages of that system. The first is that there's a Fermi level, so the topological features must near this Fermi level. The other is spin of the coupling. So can we go beyond the electronic systems to conquer this problem? For example, we can see like topological features in photons, magnons, or phonons. And the first material realization in topological phonons was actually proposed by our collaborators 22 years ago. And in that material, the phonon bands will have certain degeneracy and forming some double Weyl phonons and also Dirac phonons. And actually, if we just try to dig more into like all these vibrational modes and their degeneracy, we can find that even we look into certain like group theory textbook, it's already providing us enough like examples for these topological features. For example, in Mildred Dresselhaus's book, like she proposed like several systems with this phonon degeneracy, like graphene, like telluride, or like alpha quartz. In graphene, it's already verified that this is a Dirac phonon system, and in telluride, there's also saying it's a Weyl phonons, where in the silica, it's also a Weyl phonons. So this kind of topological phonons are everywhere as long as we have certain degeneracy or band crossing of these phonon states. Another example in that book is barium titanate, and we know that this is a famous material, and it was firstly discovered like during the World War II. And the rumor says it because like the German submarines like block all these oceans, so the American guys need to find other materials to build capacitors, and then they find barium titanate with super great like ferroelectricity or piezoelectricity. And in that case, and after the first real discovery of this material system, like people find that this barium titanate can also hold different like structure phase transition related to ferroelectricity, and also like other features such as soft mode driven structural phase transition. And this is really a famous material family. The thing is, this material family has a rich phase diagram. So at high temperature, much higher than 393 Kelvin, it is a cubic structure with AbO3 structure. And if the temperature goes down and down, we have like tetragonal phase, which is a ferroelectric phase. And after the temperature go down and down, we have an orthorhombic phase, and then we'll get rhombohedral phase for the ground state. This kind of feature, phase transition, is related to a temperature. So if we want to understand these topological features of this, we need to understand the symmetry first. So we know that a ferroelectric phase transition is related to the inversion symmetry breaking. And in that case, when there's a temperature-induced phase transition, the ferroelectric phase transition also happens because there's polar displacement of titanium and oxide atoms. And after this phase transition, the inversion symmetry will be broken as a result of this phase transition. And to understand the temperature effect in that system, we only need to consider like anharmonicity in that system. The thing is, if we don't consider any anharmonic effect, we just calculate the harmonic force constant of barium titanate, we can get imaginary phonon mode, which means that this structure is not so stable at room temperature. At zero temperature. And if we're adding more and more anharmonicity into that system, do this self-consistently, we can get the anharmonic phonon dispersion, and we can see like this, the phonon states are stabilized as a result of this anharmonicity. And as I mentioned before, this kind of barium titanate and other oxide perovskites holds plenty of properties such as superconductivity, ferroelectricity, piezoelectricity. One prominent absent in that list is topological features in the electronic structure. The thing is, most oxide perovskites are large band insulators. So to induce certain topology, it is hard for them to have some band inversion. We know we need band crossing as a result of band inversion, and without the band inversion, there will be no crossing points between these different bands. So can we go beyond the electronic structures, for example, in phonons, magnons, or photons? We first see the room temperature phonon dispersion. The thing is, at room temperature, there's the long range Coulomb interaction are there. So there will be strong LO2 splitting as a result of this long range Coulomb interaction. And these phonon degeneracy are lifted as a result of this LO2 splitting. So LO means longitudinal optical phonon, and Q means transverse optical phonon. So as long as there's a long-range Coulomb interaction, this long-range optical and the transverse optical phonon modes will be split to each other. So which means if we want to have certain topology, it is hard because there's no degeneracy of these phonon bands in the zoom center. So can we go beyond temperature, for example, in pressure-induced phase or strain-induced phase or change composition, or using light? Because we know light can provide some extra degree of freedom. As photoexcitation excites carriers into the system, the long-range Coulomb interaction will be screened as a result of this free carrier screening. And actually, there are plenty of experimental evidence and theory evidence for this photo-induced phase transition in this oxide perovskite family. Recently, there are papers on oxide perovskites and strontium titanates, and also in other oxide perovskites, and there are also theoretical work on this photo-induced phase transition. So indeed, we can use light as an external stimuli, an extra degree of freedom to control the structure phase and possibly phonon topology. So to simulate this photoexcitation effect, we can consider a delta SAF method, which is similar to the regular Kohn-Sham equation, but for the excitation state. We know that for ground state calculation, we can only consider Kohn-Sham equation. That means we can use the atomic position to generate the original potential and use this potential to solve the Schrodinger equation. And after we get the orbitals from the Schrodinger equation, we're filling them as the Fermi-Dirac distribution that these orbitals occupying the lowest energy, and then calculate the potential based on this occupation and get a new potential, use that as an input for the Schrodinger equation, and do this iteratively. For excited states, the only difference is that after we get the electronic orbital Kohn-Sham orbital from this Schrodinger equation, we can constrain the occupation of this Kohn-Sham orbital. For example, we promote electrons from the valence band to conduction band and fix this occupation of these orbitals, and then calculate the new potential based on this new constraint orbitals, and then do this self-consistently, just similar to regular Kohn-Sham equation, but it's more or less like excited version. And this delta SAF method is also non-interacting electron-hole pairs, similar to regular Kohn-Sham equations. And we know that for Kohn-Sham equation, this non-interacting Kohn-Sham equation yields the same ground states with the real interacting Hamiltonian. And we can also extend this idea from the non-interacting electron states to the non-interacting electron-hole pairs. And based on a generalized adiabatic connection scheme, we can connect the excited states of the interacting and non-interacting system to use this same Kohn-Sham equation to do the same. And as Gorlin stated 20 years ago in his paper, that Kohn-Sham formalism can be applied both to ground states and excited states. And indeed, there's one recent PRL paper saying like this photo-induced phase transition can happen for this baryon titanate using this delta SAF method. And in that paper, the tetragonal phase, which is the room temperature phase of baryon titanate, can exist in wide carrier density region from the 0.04 to 0.1 and electron per formula. So in that region, we can get the thermodynamically stable phase of the tetragonal baryon titanate. And in our calculation, we also verify these results, and we try to find the thermodynamically stable region of the baryon titanate. And we find that the originally unstable phonon modes can be stabilized by photoexcitation. And originally there was a double Weyl structure. And after we consider this photoexcitation, we can get the stabilized phonon modes. So, and immediately we can analyze the topological features of these phonon modes. So here we can see like there's 4 pair of Weyl points formed as a result between the 10th and 11th bands. And there are also no rings and no lines formed as a result of this mirror symmetry in the baryon titanate. We know the P4MM space group has certain mirror symmetry, and this gives us like no rings and no lines on that high symmetry on that mirror plane. And there's also like Weyl points. We can associate Chen number of -1 +1, and that means that Chen number always appear in pairs. So we can get topological features in that system. And if we compare the photoexcited stabilized phase, photoexcitation stabilized phonon dispersion, and the temperature stabilized phonon dispersion, we can immediately see the difference. The thing is, in the temperature stabilized phase, there are limited number, like only no rings and no lines in the system. While in the photoexcitation stabilized phase, we can have no rings, no lines, Weyl points, and also another triple Weyl points formed as the intersection between the 11, 10, and 12 bands. So if we compare the topological features in that system, we can see like the no rings can only be the no rings. There's only no rings and no lines that exist in the temperature stabilized phase, whereas in the photoexcitation phase, there are more topological features because of the strong screening that suppress the LLTO splitting. And most interestingly, we can control this topological feature by light. And the thing is, we know like this phonon dispersion is related to lattice vibrational modes, which is controlled by the interatomic force constants. And when we change the electronic states by photoexcitation, the ions will fill another electronic states. So the electronic states around the ions change. They change the energy surface around the ions. So if we play with this photoexcitation carrier density, we can get different features of topological features, such as the switch off between no lines and no rings, and the creation of new no rings here. Another thing is about the Weyl points. We know like these topological features, these Weyl points have been observed in our phonon dispersion, and this Weyl point so if we solve the Dirac equation, there are three solutions. The first is Dirac fermion, and the other is Majorana fermion, and then the last is Weyl fermions. And the people trying to find these Weyl fermions in high energy physics, but not until recently, people find that it is hard to find them in high energy physics. So not recently, people find that in condensed matter system, the band crossing of the low energy excitation, these quasi-particles will behave like the Weyl fermions. So they call this material systems Weyl metal, and we can associate the Chen number with chiralities to these band crossing points. And in the surface, this kind of Weyl points can act like the warm pole to the system. So there will be tunnel between the top surface and the bottom surface. Because of this, the Weyl points can be seen as high dimensional singularity of the system. We also find that these Weyl points in the phonon dispersion of baryon titanate can be controlled by light. So we can induce the creation and manipulation of the Weyl points. And we also find that the 001 surface of the phonons can hold certain can hold the so-called Fermi arc, and in our system it's not fermions. So we call this surface arc, connecting the Weyl points, the projection of the Weyl points with a line here. So this is surface arc, a clear sign of these Weyl points. And we also use the symmetry-based indicator group to analyze why there's a creation and manipulation of the Weyl points. And we find that these Weyl points can always be induced and annihilated as a result with different photoexcited carrier density. And to summarize, we find a system that can hold 4 different types of topological features, 2 triple Weyl points and 2 Weyl points, 8 Weyl points and 2 no rings and 1 no line. And these no lines and Weyl points can be the topological phase transition can happen, including the switch on and off between Weyl points and the creation and manipulation of the Weyl points and the switch on and off between no lines and no rings. Then, inspired by this, we go through a high throughput search in different structure phases, different composition, and the different topological features. And most importantly, try to see whether the system is dynamically stable. That means the phonon dispersion won't have imaginary phonon mode. And we also examine the external tunability, such as light, pressure, strain, and temperature. And what we find is that these topological features are everywhere in oxide perovskites, in different compounds such as lead titanate, and in like strontium titanate, in different structure phases such as the orthorhombic phase and the rhombohedral phase of iron titanate, and under different external conditions such as strain, temperature, and light. Most interesting, the topological features can change. So as we see, like here for the strain induced tetragonal phase, we can observe these three topological features, and they have the similar Fermi arc. And if we consider some structure phase transition, the topological feature will also be changed. So we propose a really great platform for this, the oxide perovskites, as a really perfect platform to study these topological features and their manipulations with light. And possibly our predictions can be verified by experimentalists. For example, there's direct observation for topological surface states using high resolution ELS, or we can direct observe these topological bulk states using inelastic neutron scattering or inelastic X-ray scattering. And here are some papers. This paper using the inelastic X-ray scattering to observe the topological feature, the bulk feature of topology. And there are also like pump probe to directly pump these optical phonon modes, and just to indirectly observe these topological features. And an outlook for our discovery is that these topological features will provide new understanding for some known effects in oxide perovskites, such as phonon Hall conductivity, or even like ferroelectricity, because we know phonon Hall conductivity and the ferroelectricity are related to a non-trivial barrier curvature. And the topological phonons also have non-trivial barrier curvature. So we may relate them together. And the other thing is that there may be no scattering mechanism, including electron phonon scattering and phonon scattering mechanism related to these topological features. So this scattering mechanism may enhance the superconductivity. So our discovery may provide new understanding to enhance superconductivity in strontium titanate. And there are also like pseudo gauge field and some one-way bulk propagating mode of these Weyl points. So based on these non-trivial transport properties, we can use light-controlled topological quantum states to do some exotic applications. For example, light-controlled neuromorphic computing. We can use like 2 light pulses to read, write, and erase the data at the same time using just 1 light at the same time, which is similar to human brain rather than modern computers that separate the memory and processor. But these are all open questions. Our discovery is just a good starting point to see all these topological features in these oxide perovskites. And the take-home message is quite clear. These topological phonons are everywhere in oxide perovskites, in different structure phases, in different compounds, and under different external conditions, such as strain, light, and pressure. And we can use photoexcitation to control these topological features. And if you are interested in our topic, you can just search our paper in topological phonons in oxide perovskite controlled by light. And I would like to thank my co-authors, Tomeo and Yuchen in Cambridge, and Tiantian and Shuichi in Tokyo. And I will also thank you for listening to this topic. And if you have any questions, feel free to discuss or comments or something.
I think I can just unmute myself, right?
Because, yeah, sure, just unmute.
Yeah. So could you please specify a bit, develop this definition of a stabilized phonon mode? When you say to stabilize a phonon state or mode, I don't remember exactly, yes, there was this
Yeah, here, right.
where the photon is emitted to stabilize. Could you please specify what is called by stabilized phonon state?
Okay, so if we don't have any photoexcitation of the system, the phonon dispersion here is like the dashed line, dash purple line here. So without any photoexcitation, we'll get unstabilized phonon mode because when we try to solve the phonon dispersion, we'll get imaginary phonon mode. That means at ground state, the structure won't be stable. And that's in the darkness or at zero temperature. And after we consider this like photoexcitation, the original, if we go along that imaginary phonon mode, we'll see a double Weyl structure. And if we add photoexcitation into the system, the double Weyl structure will change to a single Weyl. And that means the original unstabilized phonon mode will be hardened. So their frequency won't be imaginary, but become a finite.
But why was it imaginary from the very beginning?
So this system is called it's not very stable. So the thing is cubic phase. The cubic structure is not the ground state. So as you can see here, the tetragonal state is not the ground state here. So as you can see here, the ground state is a rhombohedral phase, which is certain tilting of this kind of octahedral phase. Sorry, the tilting of this octahedral around these oxygen atoms. And for the tetragonal structure, it's not so stable. So the atoms are in the saddle point of the energy surface, which can only be stabilized, for example, by temperature or by photoexcitation or by strain.
Even by temperature? Temperature seems to be pretty random.
yeah. Here you can see like at room temperature, it's a tetragonal phase. And we do calculate the phonon dispersion and find at room temperature, there's no imaginary phonon mode. So we call this stabilized.
Okay, no, maybe it somehow stretches. Okay, thank you.
Yeah, thank you.
Hello, can you hear me?
Yeah.
Hi. So I have a question about the lifetime of the stabilized structure. Do you have estimates for that?
Okay, so here we only like fix all the occupation. For example, we promoting electrons from the valence band to conduction band, and we assume like these electrons will stay in the conduction band. So that can be realized by experimentalists, for example, using some constant illumination with the same photoexcitation energy and same intensity. But in principle, the carriers will degrade, so the process is a non-equilibrium process. But the thing is, in the non-equilibrium process, we can't get a well-defined phonon dispersion because the interatomic force will just change as a result of all this carrier screening, carrier interaction. This will change the force field by the ions. So here we just assume the lifetime is infinite. But for experimental verification, maybe like we need to consider this non-equilibrium process. And these kind of topological features may be changed as a function of time, which is more exciting because we won't have constant topological features, but topological feature as a function of time.
Yeah, but I mean, so let's say the typical decay time scale for excited electrons, it's in the femtosecond regime.
Yeah, that's true.
So do you have like fast enough experiments that can prove away the gamma point?
Yeah, I think actually the phonon period is like picosecond, which is larger than this femtosecond. So for experimental verification, I would say it is best to use some constant light and in the system, or like at least let phonons have some like topological phase transition or some phonon features change first, and then like maybe carriers can radiate or form excitons. But I think in that system, like barium titanate, these are all indirect band gap. So I assume this kind of exciton or electron hole pairs will stay in their pockets for longer time.
Okay.
Yeah. And we can calculate them like electron-electron interaction time, but we just assume they're constants.
Interesting. And the other thing is about the the intrinsic lifetime of the phonons even at equilibrium. So this is very naive, right? But when I look at neutron scattering plots, they look, there is a finite resolution there.
Yeah, that's true.
Yeah. So is it would that be still within resolution to see these properties?
Yeah, I think for the oxide perovskites, this may not be the best system because there are a lot of phonon modes with different topological features. And for this inelastic X-ray scattering or neutron scattering, you need all these modes as clear as possible. And even if you conduct the experiment at super low temperature, there will still be phonon band broadening. So these broadening effects are originally everywhere. So for this kind of system, you may need some cleaner phonon dispersion. For example, you need the atoms as fewer as possible, so the phonon dispersion will be clean. And so the oxide perovskites may not be the best system, but there are also other candidates for these degeneracies.
Okay. Yeah. So I have one more question. So in your calculations, you showed us the bulk bus structure.
Yeah, that's true.
Here for phonons, do you also have this concept of bulk boundary correspondence, and what type of signatures you get in finite size systems?
Yeah, I think so. I calculate like the surface mode, like the surface projection, to see whether there's like Fermi arc or surface arc connecting different Weyl points. And indeed, if you can see like here, there are two Weyl points with different chirality, and their projection, there's a surface arc connecting each other. So it's kind of verified using the Fermi arc to verify the existence of these Weyl points.
Okay. Thank you. It's very interesting.
Thanks. Yeah. And we can actually calculate like the surface states, but we don't show them here because they're like mixed with all these bulk modes. So we just show like the surface arc.
Yeah, thank you.
Thanks.
Hello.
Hello, Matthew.
Hi. Thank you for your talk.
Thanks.
I was thinking about graphene and how the Dirac point gives rise to a host of very large nonlinear responses to light. And these kind of nonlinearities, like four-way mixing, harmonic generations, so on, can we expect the same nonlinear properties for the phonons, the Dirac phonons or Weyl phonons?
I actually don't know too much about all this linear. I think do you mention like they're related to the electronic states because these Dirac cones are like some metallic or some excitation related, like plasma, or it's like.
Yeah, it's supposed to be. I also don't know so much, but it's supposed to be directly related to the linear dispersion of the electrons.
Okay, so if that's the case, I think for oxide perovskites, they're insulators, so they won't have like too much like this Dirac cone in the electronic band structures. So I would say probably it's not so, but I do find a lot of papers saying like phonon nonlinear, I don't know how to pronounce, but there's some papers saying like this oxide perovskites can code this topological nonlinear features.
Okay.
I think Nicholas Spalding has some work on this.
Maybe can I also ask a question?
Sure. Hello.
Thank you for your talk.
Thanks.
So this phonon mode, this phonon has some wave number along the dispersion, right? And can be anywhere between, necessarily at the gamma point. Is that correct?
Yeah.
Then how do you interact with this phonon mode if it's not directly at the gamma point? In what ways could you interact so that you can actually make use of its topological properties?
Okay, so I answer this in two ways. The first is we can find topological features at the gamma point by finding the like certain space group And these oxide perovskites, they just don't have the space group for the gamma point topological features. Although there are no lines or no rings at the gamma point, these Weyl points are not. Actually, all the Weyl points are not. I think nearly all the Weyl points are not in the gamma point or high symmetry point. But the thing is, we can make them as close to the zoom center as possible. So there's still a chance to observe them. And another point I want to mention is we can use some indirect way to make use of these topological features. For example, these topological features are related to some non-trivial barrier curvature, which may have some phonon hole conductivity effects. So we may observe certain transport properties using these topological features, although they are not at the gamma point to be observed. And there are also other ways to observe them rather than exciting the gamma point phonons. There are also ELS to see this zoom boundary or the phonon dispersion directly.
Okay, thank you.
Yeah, thanks. And other questions? If you have any questions, you can also send me an email in the beginning. So you can also send me an email if you want. We can have discussions further or some this related topic, because this topological phonons, we still do plenty of new works in these oxide perovskites and also topological phonons in these systems. Any other questions? If there's no further questions, I'll just end the session. It is really nice to meet you all, and thank you for listening and for the question and for the comments.
And thank you for the talk.
Thank you for the talk.
Nice talk.
Have a good day.
You too.
Thank
Bye.
you for the talk. Thank you.
Thanks.